In this video, we'll talk about solving radical equations. A radical equation is an equation containing radical signs. For example, equations like this. How can we solve those equations? Let's see the first one. Here we can just guess a number, because we know that square root of 16 is 4, so we can guess that x equals 16. But what if this number is not a perfect square and maybe it's not so easy to guess? How to do it methodically? Well, we are after the x, so what we need to do is undo the square root. How do we undo operations? By applying inverse operations. So in this case, it is enough to square both sides of the equation. The square will cancel the root, and that's how we obtain the x by itself. And 4 squared is 16. So yes, our guess was correct. Let's see the next equation. How do we solve this one? Well, the situation is a little bit different than in the previous one, because if we square the whole left-hand side, we would have to apply perfect square formula, which leads us to 3 terms, with the middle term still involving a root, isn't it? So the idea here is to isolate the radical by itself on one side of the equation, like in the previous case. Okay, what we could do here is to move this whole radical term to the other side of the equation and make it positive. So we would have root of 2x on the right-hand side, and then go with 3 minus 1 on the left-hand side. So it's actually 2. Now we're ready to square both sides of the equation to cancel the root. Therefore, we obtain 2x equals 4, and after division by 2, x by itself would be just 2. We may want to check if our possible root is actually good for the original equation. So let's check. Plug in the x value 2 to the original equation. We will get 3 minus root 2 times 2 here, and equals 1. Question mark. Is it true or not? Well, we have 3 minus root 4 is really 2, so yes, it confirms that's true. 1 is equal to 1. Therefore, we are sure that the solution is x equals 2. Let's see the following example. Root of something is equal to negative 1. Well, if we apply the same strategy as before, squaring both sides of the equation, let's see what will happen. On the left-hand side, the square cancels the root, so we have 2x plus 3. And on the right-hand side, negative 1 squared is just 1. So we end up with a linear equation, which is easy to solve. Here we have 1 minus 3, so it's negative 2. And dividing by 2x becomes negative 1. Is that our solution or not? Let's check. If I plug in negative 1 for x, on the left-hand side of the equation, I have 2 times negative 1 plus 3 under the root. On the right-hand side, I have negative 1. Are these two sides really equal or not? Root of negative 2 plus 3, so it's really root of 1. Is that equal to negative 1? Of course it's not, because this side is equal to 1 and that side is equal to negative 1, so they are not equal. That means that our possible root is actually not a true root for the original equation. Therefore, the final answer in this case would be no solution, because negative 1 doesn't work. Notice that we could come up with this answer in the very beginning without doing all these calculations. It was enough to observe that on the left-hand side we have a root of something which is never negative, so it's non-negative. And on the right-hand side, we have something that is negative. Obviously, a number that is positive or 0 is never equal to negative. That's why we could claim at once that the original equation has no solution, without doing all these calculations. But if we didn't notice that, the important step in solving radical equations will be to check the possible solutions that we obtained. Check if they work, because some of them may not work. So the checking part is critical here. Okay, let's see the last example. Here we have a cubic root of x equals to x. Well, we want to get rid of the cubic root somehow, so we could use similar strategy as before, we need to undo the cubic root by cubing both sides of the equation. Okay, so the power 3 cancels the cubic root. We end up with x on this side and x cubed on the other side. And now there are two possible ways of approaching this problem. I would advise that we always move everything to one side and try to factor. So, for example, if I move x to the right but start writing it from the left, like x cubed minus x, and since x went to the right, on the left-hand side will be 0, right? So if we rewrite it from the left to the right, 0 will be here. And now factor. Solve it by factoring. So if I factor x out, I end up with x squared minus 1 equals 0. And then this is difference of squares, so let's factor it further into two conjugate brackets. Therefore, the possible roots are x equals 0, from this bracket is 1, or from that bracket is negative 1. We have three possible roots. It's easy to check that all of those numbers work, because cubic root of 0 is 0, that checks. Cubic root of 1 is 1, that also checks. And cubic root of negative 1 is also negative 1, which means all three roots check. Therefore, the final answer is x equals 0, 1, and negative 1. Not a problem here. However, let's see what may happen when instead of factoring, we decide to divide this equation by x at this stage. Let's write it down on this side here. The left-hand side will be 1, the right-hand side x squared. And then if we take square root of this equation, we may end up with x equals just 1. Okay, so what's going on? Solving it this way, we obtain just one root instead of three roots. So where did we lose the other two roots? 0 and negative 1. Well, the answer is first root was lost when we decided to divide by an x, because anytime we divide by something, we have to remember that this something can't become 0. So this step is allowed only if x is different than 0. Okay? So we would have to consider the case when x is equal 0 separately. But this is very easy to overlook. So that's the first reason why it's safer to move everything to one side and solve by factoring, rather than dividing by some expression that may turn out to be 0. Okay, so that explains losing 0. What about negative 1? Well, the second possible mistake is when we take square root of x squared. Remember, square root of unknown square is absolute value of this unknown. So if we overlook this absolute value, we are losing another root. If we remember the absolute value, the final answer would be the same. It would be either 1 or negative 1, right? Because of these two possible traps, my suggestion is solve equations by factoring. Factoring is a safer road. Okay, I'm going to erase this other possible way of solving. So here it is, three roots. Let's look at the steps that we need to take to solve any radical equation. We'll observe those steps by looking at this example. So the first step would be to isolate one radical on one side of the equation. Isolate means leave it alone without any extra addends and possibly with positive sign in front of it. So in our case, we want to leave this radical on the left-hand side and bring the 5 to the other side. So that's the first step. Next, we are going to square both sides of the equation in order to annihilate this root. So we're squaring the left-hand side and squaring the right-hand side. Obviously, if we deal with nth degree radical, we need to raise both sides to the nth power. Remember to use perfect square formula when squaring a binomial. Square of the first plus or minus double the product and square of the last. So don't forget the middle term. Overlooking this term is one of the most common mistakes. Okay, so on the left-hand side the root disappears and we have just 5x minus 1. On the right-hand side, square of the x is here, minus double the product, 2 times 5 is 10 times x, and plus square of the last. Now when we have this polynomial, we want to arrange everything to one side and collect like terms. Since the positive x squared is on the right-hand side, I'm going to start with this side first. So it will be x squared. We bring the 5x to the right, becomes negative 5 and negative 10, so it's negative 15x. And we bring the negative 1 to the right, makes it plus 1, and 25, that's 26. Everything equals to 0. So after we collect like terms and arrange everything in order, in our example, we have a nice quadratic polynomial. There's no more radicals, but if we still have a radical, for any chance, we repeat the first two steps until we clear all radicals. So if there is any radical left over, again, isolate this radical, square it, and make sure that we don't have any radicals in the end. So after this step, we're supposed to end up with a polynomial equation, which obviously we need to solve. Usually it's a linear or quadratic equation, but it could be some higher degree polynomial as well. In our case, it's a quadratic equation. We can go through factoring. So we prepare two brackets, x and x, and we're looking for two numbers that will give product 26 and sum 15. That happens to be 13 and 2. So after factoring, we read the possible roots from each bracket. From this bracket we have 13 and the other bracket gives us 2. Okay, that's not the end. Since we are solving radical equation, we are obligated to check if those possible values are true roots or not. So check the possible solutions if they work for the original equation. If not, drop them. Okay, so we check. If x is 13, we plug in 13 to the original equation. So we have root of 5 times 13 minus 1 plus 5 outside. Is that equal to, question mark, 13? Okay, 5 times 13 is 65 minus 1 is 64. So root 64 is 8. 8 plus 5, yes, it is 13. So this root is confirmed. What if x is 2? Again, plug it into the original equation. Root of 5 times 2 minus 1 plus 5. Is that equal to 2? Let's see. 10 minus 1, oh, that's 9. Root 9 is 3. 3 plus 5, that's 8. This is not 2. Therefore, 2 doesn't work. We have to exclude it. So we're ready to give the final answer. State the final answer clearly. This is part of our job, decide which out of these two numbers is actually root. Sometimes we may have no solution, sometimes only one number works, like in this case, sometimes both numbers will work. We always need to check. Okay, let's work on these two examples. Here one root is already isolated, so let's square both sides. On the left hand side we have just 5 minus x. On the right hand side, when we square the 2, we get 4, and square the root, we get the radicand, just negative x. Okay, now we have a linear equation to solve. After multiplying 4 by negative x, we have negative 4x. Bringing the negative x to the right, it becomes positive x, and let's stay with 5 on the left hand side. So on the right hand side we have negative 3x, and on the left hand side 5. Therefore the x by itself after division becomes negative 5/3. It's kind of ugly number, but the roots doesn't have to be always pretty. Okay, let's check if this root works. So if we plug in negative 5/3 to the left hand side of the equation, we have 5 minus negative, that becomes plus 5/3. Is that equal to 2 times root of negative negative becomes plus 5/3? Let's see. We may want to put this 5 under the same denominator 3, so it will be 15 plus 5, it's 20/3 under the root. And here, if we bring the 2 under the root, it becomes 4. 4 times 5, it's also 20/3. So yes, it looks like this root works. Therefore, our final answer is x is equal negative 5/3. Even though it wasn't very pretty, it is still a root. Great. Let's see the next example, cubic roots. Let's cube both sides to annihilate the cubic root, right? Okay, so we have 2x minus 6 equals 4 minus 3x. Again, if we bring the x's to one side, this time to the left side, it becomes 3x plus 2x, it's 5x. And let's bring the 6 over to the right side, it becomes 6 plus 4, so it's 10. After dividing by 5, we get x equals 2. So, is that a true root or not? Let's check it. By the way, if we deal with a cubic root or any odd degree roots, usually we don't even have to check because those numbers will work. The only danger is when we deal with even degree roots, because the operation of raising an equation to an even power sometimes does not produce an equivalent equation. So we could get some extraneous roots. With odd degree radicals, this doesn't happen, so the checking is not really essential, but just for the sake of being on the safe side, we can check it. So, cubic root of 2 times 2 minus 6, is that equal to cubic root of 4 minus 3 times 2? Here we have 4 minus 6, so it's negative 2. We have cubic root of negative 2. Over there we have 4 minus 6, so it's also cubic root of negative 2. That means they are the same, so yes, the answer is correct. X equals 2. Let's look at this example. Here we deal with two roots on the same side, so the idea is to isolate a single root at a time. Therefore, I'm going to move this root to the right-hand side. So we have root of x plus 1 equals 2 plus root of x minus 1. And now we're supposed to square both sides, right? The square on the left-hand side causes that the root disappears, that's fine. But on the right-hand side, we really have to be careful. We need to apply perfect square formula because we have two terms, right? Okay, so let's do that. Square of the first term, which is 4, plus double the product. 2 times 2 is 4 times the root. 4 root, that's our middle term. And then plus square root of the last term, which is x minus 1. Now, we still have a root, but on a single root. So let's leave this root by itself on one side. We're going to isolate it again and bring everything else to the other side. In the meantime, we can notice that these two x's on both sides of the equation can be cancelled. It's like subtracting x from both sides of the equation. And now let's bring all the numerical values to the other side. So we have 4 minus 1, it's 3. To the other side is negative 3. Negative 3 and 1 is negative 2. So we have negative 2 here and we have 4 root of x minus 1 on the other side. Well, in this case, without any further calculations, we can notice that this side is negative. And that side, because of the root that is multiplied by positive 4, is never negative. So this side is non-negative. Okay? Therefore, they can't be equal. Because of this fact, we can already state the final answer as no solution. So in this case, there is no need to square both sides again and solving for x and then checking it. You're welcome to try it, but in the end, you will see that no possible solution will actually work. So anytime we have a square root on one side and a negative number on the other side, we won't have any solutions. Sometimes our radical equation can be hidden under those rational exponents. So the first thing that I would suggest is to rewrite the whole equation in a way that you can see the radicals without the rational exponents. In the meantime, since we want to isolate one radical, let's bring this radical to the right-hand side. So we will have root of 3x plus 4 on the left, and then 2 plus root of 2x minus 4 on the right. Let's raise both sides of the equation to the square, and then we have 3x plus 4 on the left, and here we need to apply perfect square formula. Remember, 3 terms. 2 square is 4 plus double the product, which is 4 times the root, and plus square of the root, which means root disappears and we have just the radicand. Now, since we still have the radical sign, we isolate it again, leave it on the right hand side as it is, and we are going to bring everything else to the left. So 3x minus these 2x, so it's just 1x. These two 4's are cancelled, and that 4 goes to the left, it becomes plus 4. Now we are ready to square again. Square both sides. And one more time, apply perfect square formula to the left hand side this time. So square of the x squared plus double the product, which is 8x, plus last term square, which is 16, equals square of the 4, which is 16, square of the root, has to be written in a bracket because of this multiplication by 16 here. So in the bracket is 2x minus 4, right? Okay, let's release the bracket. So we have 32x minus 64. Okay, copy it, copy the rest, and then bring everything to one side. So we have x squared minus 32 plus 8 is minus 24x, right? And then 16 plus 64 is plus 80 equals 0. Let's continue here. We're going to factor this trinomial. Can we factor it? We're looking for two numbers that will multiply to 80 and add to 24. Well, it's 4 times 20, isn't it? So we can go x minus 20 times x minus 4 equals 0. Therefore, our possible roots are x equals 20 or x equals 4. As usual, we need to check our possible solutions. So if x is 20, what do we have? Well, let's use original equation. Square root of 3 times 20 plus 4 minus square root of 2 times 20 minus 4. Is that equal to 2? Okay, let's see. 64 and root of it is 8 minus 40 minus 4 is 36. Root of it is 6. Yes, 8 minus 6 is 2. That confirms. And now if x is 4, let's do the same. Square root of 3 times 4 plus 4 minus square root of 2 times 4 minus 4. Is that equal to 2? Okay, we have 12 plus 4, which is 16. Root of 16 is 4. Minus root of 8 minus 4 is root 4, so it's 2. Yes, it is 2. So this solution also works. Therefore, our final answer for this question is x is equal to 20 or 4. There's two possible answers. Finally, let's solve some formulas that involve radicals for a given variable. In example A, we're solving this formula for L. So let's mark the L in different color, for example in red, so it will be easier for us to focus our minds on that letter. Okay, to be closer to this L, what we need to do is get rid of the 2 pi first, and then gradually get rid of the radical sign, and finally get rid of the division by 32. So that's the plan. Let's divide by 2 pi first. Therefore, the 2 pi will go to the other side as a denominator, right? That equals square root of our L over 32. Now, to get closer to L, we have to undo the radical. So we are squaring both sides of the equation. Therefore, we obtain t squared over 4 pi squared on the left-hand side and L over 32 on the right-hand side. Okay, we are nearly at the end. The last thing that we need to do is to get rid of 32, which means to undo this division, we need to multiply by 32. 32 will go to the numerator to the other side. Let's write it here. We'll get 32t squared over 4 pi squared, and that's our L. Now let's reduce 32 with 4. That gives us 8 in the numerator. So the final answer is L equals 8t squared over pi squared. Here it is. Let's do the same for the second formula. This time we're solving for r, and r is in the denominator. So there's quite a few things to take care of. We have to get rid of this leading coefficient in front of the root. Then we need to get rid of the radical. And finally, we need to make sure that r is in the numerator. So we need to flip this fraction somehow. Okay, so the first thing would be to get rid of this 2 pi from the denominator. This really means that we need to multiply the whole equation by 2 pi. Or sometimes I refer to it as teeter-totter. If we move something from the denominator, it goes to the other side as a numerator. It really changes its level, right? So the 2 pi goes to the numerator times n. And then on the right hand side we still have root of a over our favorite r. Now to get rid of the radical we need to square both sides of the equation, right? And we end up with 4 pi square n square on the left hand side. The root is gone and the right hand side becomes a over r. Finally, what we need to do is to leave r by itself. We can do it in two ways. We can either write reciprocals of both sides of the equation, that will cause that r goes to the numerator, or we can interchange the spots for r and the whole expression on the left, because formally we're multiplying this equation by r and we're dividing it by 4 pi square n square. So we basically swap those places. R goes up, we stay with a, and the whole expression from the left goes down to the other side, right? Here it is. That's the final answer.